Okay, so what happens when we get these charges close to each other? You have to go kind of quick. I don't have much battery left. I already mentioned that they're very similar to gravitational forces. We're not going to do these examples right now. Maybe not at all. But you remember I said F equals big G, M1, M2. This is the gravitational one, R squared. Look at this. This would be your constant, just like G was. Your two charges, the strength, and then the distance between the two. Okay? This K here, K, was known as Coulomb's constant. I'm not sure if you could actually read that. I really want to get into this idea of electric fields. Okay? I don't need to worry about all this. This is doing the calculations. Okay. So, you could read through this. I always think of magnetic fields. So, if you have a really strong magnet, and they're not the same as electric, but it's you know, parallel. You get a really strong magnet, and you actually drop iron filings, you actually could start to see the field lines form. A very similar thing happens with electric fields. Here they are right here. So let's say we have a positive charge. We would draw electric field lines moving away from the positive charge. So this is just a standard thing that we've done in physics, and I don't know when they decided to do this, but we always act like there's this little tiny positive charge. Okay, so if you put a positive up to a positive, this is called like a test charge. And we always say it's positive. It's just conventional in physics to do that. So if we put a positive charge up to a positive, it would push it away. That's why our field lines are away. If we took our little test charge, which is positive, up to a negative, it would pull it towards it. And the more of these lines that you see, the stronger it is, okay? And that's all it's showing right here, okay? It's also what it mentions right there about the strength. So yeah, for a negative, it'd be towards because our test charge is positive. Positive charge, it's away because it's likes repel, okay? Or how about if you have two? So down here, let's say we had, can't even tell which one's what. Yep, this one's actually a negative charge and a negative charge. Okay, so if we had a little positive test charge being put in there, it'd be pulling it towards each one. And you could see here, hopefully you could see that these lines are actually pulling towards each charge. Now, the more charges we have, the more complex things start to look. All right? One of the easier ones, and it just seems like that you'll see a lot, is if one's positive and one's negative. If we have our little positive charge in here, it'd be pushed away from the positive and towards the negative. And you would just see it start to look like this, and it would kind of bulge out and this and that. The stronger the positive and the negative are, the more of these lines you would start to see. Okay? Stronger charges, stronger fields, more field lines. Okay? And that's pretty much it. Okay? So this here's a negative and negative. How about if we had a positive and a positive? Let's just think about that. If we put a positive charge in here, okay, both of these would be trying to push that positive away. So we try to push it this way, but then this one would also be pushing, so it would kind of go out. They'd be fighting against each other. And so see this one, how it's pointing towards them, towards, because it's negative, negative. If they're positive, positive would be away, away, away. So it'd look exactly the same, but just in a different direction. Okay, now you could actually calculate the strength of those fields and everything. But for now, it's just a general background. And you could look in the book about this. This gives some extra information about they must begin at the positive charges and terminate at the negative, okay, which just makes sense. Or at infinity, if we had a point charge, it would terminate out here at infinity somewhere. Number of field lines leaving a positive charge entering a negative is proportional to the magnitude of the charge. So the more lines, the bigger the charge. Okay? You can't see this, but I'm just reading it. Strength of field is proportional to the closeness of the field lines. So imagine we have this drawing right here. Okay? Let's just imagine we have this surface area. Try to imagine like 3D. However many lines are passing through that. Okay? That's how strong it is. Now think about it. If we had like, let's say this is like 1 centimeter. If we had the 1 centimeter here, you'd have more field lines, meaning it'd be stronger here than out here. All right. And the direction of the electric field is tangent to the field line, which basically just follows the arrow, right? That's a tangent. So if it's here, it's pointing out that way, it's curved because we have like positives and they're like this. At any point, we just draw a tangent line. And that would be the direction of the electric field at that point. So that's a rough introduction to electric fields and electricity. And more importantly, I feel like, is resistance and resistors and parallel circuits and series circuits and that sort of thing.